Hello, everyone. Welcome to the International Methods Colloquium. The IMC is a periodic online interactive seminar discussion on the application of quantitative statistical methodology to the social sciences, sponsored by Wake Forest University and previously sponsored by Rice University and the National Science Foundation. This week's speaker is Matt Blackwell of Harvard University. He'll be giving a talk entitled Telescope Matching, a Flexible Approach to Estimating Direct Effects. Matt's talk will last between 30 to 40 minutes, after which point we'll take questions from the audience. You can ask a question using the Zoom Q&A button that appears at the bottom of the webinar window. You can ask questions at any time during the talk, but I'm going to hold all the questions until the end unless they're very clearly clarification questions, in which case I will break in. A link to Matt's paper and slideshow will be available in the Zoom webinar chat window so that you may refer to it throughout the presentation, and I will post those links right after we get started. Now I'd like to welcome Matt Blackwell to the IMC. Matt, welcome.
Great. Thanks, Justin. Thanks for hosting this, and thanks for having me on. This is really fun. So today I'm going to be talking about this paper called Telescope Matching that is a co-authored project with Anton Streznev, who is a recent graduate of our department and is now a postdoc at University of Pennsylvania. And the idea behind this paper is that what we're interested in doing here is estimating the direct effect, the direct causal effect of some treatment net some kind of mediating value. So the effect of some treatment that's not due to some particular downstream cause. And so this is something that we care about a lot in the social sciences for a variety of reasons. A big reason why we care about this is due to causal mediation. It's a direct effects and indirect effects are a big part of how we think about mediation quantities. But it can also be useful for estimating causal mechanisms, thinking about is there any remaining effect of this treatment once we kind of net out a particular downstream cause. And in some other work with Adam Glenn at Emory, we've talked about how to use these kinds of direct effects to estimate the effect of lagged treatments in time series cross-sectional data. So there's a lot of different situations in the social sciences and political science where we care about estimating these direct effects in kind of a causal inference setting. And so there's a lot of different ways that we could think about doing this direct effects estimation. So if we just do kind of a standard approach where we take either a standard regression model or a matching model where we just kind of control for that post-treatment variable or match on that post-treatment variable, what we could end up doing is inducing post-treatment bias. That's going to bias our causal effect estimates or direct effects estimates away from their true value. And there have been other methods proposed for estimating these kinds of direct effects, things like sequential G estimation, different kinds of weighting methods. But in general, we're going to talk about this a little bit, that these are going to be really model dependent, right? They require us to have pretty solid models for different conditional expectations or different probabilities, conditional probability statements in our estimation. So that's going to be problematic. So what we're proposing is an alternative that we're calling telescope matching, and it's a consistent estimator for these kinds of direct effects that I'll kind of define more formally here in a second. What's nice about this procedure is going to avoid the kinds of post-treatment bias that we see kind of using traditional regression and weight matching methods. And it's going to be robust to some model misspecification if we're not necessarily getting the exact model right. So the matching is going to help us be robust to those kind of small errors that we make in specifying our regression functions. And what's one very nice property about this is it carries over all of the logic that we know from a standard matching procedure to kind of a two-step procedure that is relatively easy to implement. So that's the basic idea that we're going to talk about today, is kind of implementing this idea of this telescope matching and how it works, what its properties are, and applying it to a particular data context. So this is the roadmap of the talk I'm going to give today, which is going to first start with just kind of defining what these direct effects are and talk about why they're difficult to estimate in most settings. And then I'll move on to talk about our own approach, this telescope matching that I just discussed. I'll then go on to kind of show some simulations that show what can happen when you have misspecification and how this telescope matching is able to avoid kind of the problems of misspecification. I'll talk about an application, and then I'll wrap up with some concluding thoughts. So the first thing is the difficulty of direct effects. So why is it hard to actually estimate these things? It seems like it should be easy. We just kind of put things in a regression and everything should be fine. So just to start off, I'm going to kind of introduce kind of some notation and a setting so that we're all on the same page about kind of a particular example that we can talk about. So the empirical setting that I'm going to talk about at the end of the talk is going to be the effect of some sort of frame, a frame of media accounts about immigration. So in particular, we're going to think about a particular binary treatment. We're going to label that A, and the binary treatment can either be a negative frame or a positive frame. Right? So we might have some media accounts of immigration that take on a positive tone and some that take on a negative tone, that frame the particular immigrants or the immigrant groups in positive or negative ways. Now, we might be interested in a particular mediator or a particular downstream effect of that frame, which is going to be, say, some sort of psychological state. In the paper that we're going to talk about today, that's anxiety. So it might be the case that a negative or positive frame induces a high or low level of anxiety in the respondent that's reading these media accounts. And we're going to label this M sub I as being the mediator in this case. And then we're going to think about a particular outcome. In this case, for this experiment, it's going to be the outcome is just support for immigration. So to what extent does having a negative versus positive frame affect your level of support for immigration? And the kind of key trick with a lot of these causal inference techniques or causal inference methods is that we're going to be defining a particular potential outcome. And these are just kind of counterfactual outcomes or potentially counterfactual outcomes that are, so the labeling here is yi of am, little a, little m. And what that's saying is this is the potential outcome, or what would have happened to unit I, that their level of support that they for immigration that they would have had if we were to go in and set them to have a particular level of treatment A and a particular level of the mediator M. So if we could intervene on both of those things and set those values, we would see that particular potential outcome. Okay, and so that's the basic idea. And then a lot of what we're going to think about is thinking about the differences between different types of potential outcomes are differences between, say, the factual and counterfactual worlds, and that's going to be our definition of causality. So in particular, we're going to think about, in this paper, the quantity of interest that we're going to define is called the average control direct effect. And that's going to be the average effect of manipulating the treatment while fixing the mediator to some level little m. So in particular, you can see in this definition, right, this is the yi of 1 little m minus yi of 0 little m, and we're taking that expectation across units. And so this is basically the effect of moving everyone from control to treatment while fixing their level of the mediator particular value. So this is a pretty easily identifiable and kind of estimable quantity if both the treatment and the mediator are randomized. But in a lot of studies, we are going to have M be observational in the sense that we don't get to directly manipulate M, the mediator, but we're actually just going to observe it as part of the process of doing an experiment or doing an observational study. So that a lot of times this is kind of seen to be problematic because this is say an experimental context, because this is when we go to direct effects, we're moving from a really nicely identified, clean randomized control trial with a randomized treatment to something where we actually have to do we're creating an observational study within that randomized experiment by starting to analyze things based on M. So it gives some people in the experimental community some pause, but we're going to think about here, what can we do when we're in that situation? Okay. So whether or not we have a randomized experiment in our observational study, as soon as we have, we're looking at M being observational, we need to start thinking about potential confounders for the different relationships of interest. So in particular, we're going to think about a couple different possible confounders. So I've labeled, here's a kind of a graph that gives you some sense of the causal ordering of things. We have treatment affecting the mediator and the mediator affecting the outcome, and then also perhaps a direct effect of treatment on the outcome. That's the quantity of interest in this particular case. We're going to think about two different sets of confounders in the study. So the first is going to be a set of baseline covariates or baseline confounders, and those are going to be things that can confound the relationship between the treatment and the outcome, and they can also confound the relationship between the treatment and the mediator, and between the mediator and the outcome. So these are just things that are treatment, pre-mediator, pre-outcome. These are just baseline covariates before your study gets started. The next set of covariates are the tricky ones, and these are what we're referring to as intermediate covariates. We're calling them Z in this case. And these are going to be values. These are going to be covariates that confound the relationship between the mediator and the outcome, between M and Y in this case, but they are causally affected by the treatment. So they're post-treatment, but they're pre-mediator, and they could possibly confound the relationship between the mediator and the outcome. And these are going to give us a lot of headaches in these studies because they're very difficult to kind of control for these Z's in the appropriate way. So before I even get to that, let's talk about what are the assumptions that we're going to make in this paper just to get them out of the way. And the first one is going to be a sequential ignorability assumption, which you can also think of as just two separate no omitted variables assumptions, kind of in a standard regression context. So ignoring the kind of the math here, you can just think of this as first, there's no omitted variables for A, for the regression of Y on A, given the set of baseline covariates. So this just says that if I ran a regression of Y on A and X, I could interpret the effect, the coefficient on A as a causal effect. And then the second, kind of a similar no omitted variables assumption for M, given A, X, and Z. So if I were to run a regression of Y on M, A, X, and Z, again, I could read off the coefficient on M as the causal effect of M. So this is basically two standard selection on observable assumptions right in a row. One for treatment and one for the mediator. And then the other kind of assumption we need to make in this case when it comes to for this matching scheme that we're going to come up with is one of what's called positivity, or in the matching literature, this is sometimes called overlap, which basically says that there are no parts of the distribution of these covariates such that there's zero probability of treatment or zero probability of the mediator. Right? So the distributions are not, they overlap in some sense. It could be very small, but there is some overlap. Okay, so what's the problem? So I've set this up. I have these two. It seems like if I have these two kind of no omitted variables assumptions, it should be very straightforward to kind of estimate the direct effect of treatment in this case. But it turns out that this is going to be very difficult. And the reason is if we think about taking a naive regression or matching approach. So we're going to regress Y on A, X, M, right? And then we're going to think about or match on those quantities. And then we're going to think about what are we going to do about the Z's? Well, so I could omit Z from that regression or that matching technique, but that's going to induce omitted variable bias for the relationship between M and Y. It's going to bias my estimates of the effect of M. I could also control for Z in this regression, but then what I'm going to end up with is post-treatment bias for treatment, right? Because I'm controlling for something, the intermediate covariates that are causally affected by the treatment, and that's going to lead to selection bias in our estimates of the effect of A. Right, so this is kind of puts us in this between a rock and a hard place in terms of there's no way in a single regression model or a single matching model to be able to do both of these things at the same time. And furthermore, it's problematic because these two biases don't necessarily have to be in opposite directions. They could be in the same direction. So even if you say do it both ways and find that they're both positive or they're both negative, that doesn't necessarily mean that the true direct effect is anywhere between those two values. So that leaves us kind of with a bit of a problem here. That we need to get around. And so there's been a number of approaches that have been developed, mostly in biostatistics, to deal with this issue where you have post-treatment confounding in this way, these intermediate covariates. One broad class of models is called structural nested mean models. It's a bit of a mouthful. But they're basically, you can think of these as being a set of multi-stage regression techniques that allow us to identify these effects, right? So I said on the last slide that you couldn't necessarily just use a single regression model to be able to identify these effects, but it turns out if you kind of use multiple regression models nested in the correct way, you can do some damage here. But one downside of these is that these are going to require correct modeling assumptions for the regression, say, of Y on X, A, Z, and M, right? So that long regression, and then also a correct specification of the short regression, just the Y on X and A, right? So in some sense, this is similar to in the single shot case when we're just estimating a single treatment effect. This is similar to the assumption that you have to have the right regression model. but now I need two of them. Another broad set of models that we could possibly use, or a broad set of approaches, is called inverse probability of treatment weighting. And this doesn't rely as much on the specifying a regression outcome, or sorry, a regression model for the outcome, but instead this is going to focus more on estimating the probability of the mediator and the probability of the treatment given the covariates, right? So this is, in this case, you're going to need to specify correct kind of logit or models for the relationship with M and A as outcomes and the covariates as the X and the Z as covariates, right? And so that also requires correct modeling assumptions for both of these two quantities in order to estimate the kinds of direct effects that I mentioned before. So these are both totally valid approaches, and I think they can work in a lot of contexts, but one problem is going to be that you need to be able to specify these correct models. And so part of the motivation for what we're doing here is trying to come up with a new way of a new matching technique to kind of supplement these two approaches that allows us to kind of weaken some of these modeling assumptions in certain contexts. Okay, so what is our approach? What is this telescope matching? So telescope matching is going to be basically a two-stage matching procedure. Again, I kind of hinted at this earlier when I said that you couldn't do this all in one matching approach or all-in-one regression approach. So what we're going to do is we're going to break it out actually into two different stages. One to kind of estimate the M effects and one to estimate the A effects, and then we'll put the two together in order to come up with our estimate of the direct effect. So the first thing we're going to do is, and you can think of this as basically two standard matching approaches, with some clever transformations of the outcome. So the first thing we're going to do is we're going to pretend for a second that we're going to do a standard matching where we treat M as the treatment, right? So we're going to match, we're going to find M equals 1 units that are similar to M equals 0 units on values of Z, A, and X, right? So we're going to treat those things as the covariate set. We're going to use those matches to impute the missing counterfactual. So in particular, if we wanted to say estimate the control direct effect when M is equal to 0, then what we need to do is we need to impute for people that had M equals 1, we need to impute their missing values of the potential outcome, what they would have had if they had been assigned to, or if they had had M is equal to 0. So when we do that matching, we can use the matches to impute those missing counterfactuals, and I'll talk more about that. And then once we have those missing counterfactuals, we can do another kind of standard matching process where we match A, the treatment, on X. So we find A equals 1 units that are similar to A equals 0 units on values of the baseline covariates. Right. And then again, we do a similar kind of imputation technique there, combining these two steps in order to estimate the control direct effect under, say, M equals 0. So that's the basic idea. We're going to just basically do two standard matching techniques and then impute them in kind of impute the missing potential outcomes in specific ways in order to get these missing counterfactuals. So let me just talk a little bit more about what that looks like. So I'm going to kind of use this example of a table here where we have a set of units. We have their values of the observed data, which is going to be Y, A, M, X, and Z. And then we have a series of potential outcomes, right? And so what this person would have responded to under various combinations of A and M. And remember that the number in the first column here is going, or in the first part of the potential outcome is A, and the second is M. So here's unit 1. Unit 1 is treated and has M equals 1. So this is a treated unit with high anxiety, for instance, and has an X of 10 and a Z of 3. All right, and just you can see in the potential outcomes, we get to observe this unit's value of the potential outcome under 1, 1, but we do not get to observe any of their other values of potential outcome, right? Because we only get to see them under A equals 1, M equals 1. Unit 2 is treated but has a low anxiety, so M is equal to 0. And so we don't get to observe 1, 1 for this person. We get to observe their potential outcome under 1, 0. Right? That's what we observe. Right, and we can do this for, here are 6 units total, 3 of which are treated, 3 of which are control, and you can see that in each, that they all correspond to observing different potential outcomes. Okay, so what we like to be able to do in order to estimate the control direct effect of treatment is to take the difference, the average difference between these two columns that are currently in red, right? So if we wanted to estimate the effect of treatment fixing m to 0, right, for let's say low values, what's the effect of a negative immigration frame for when we have low anxiety? We want to be able to just take the difference between these two columns and take the average of them, right? But unfortunately, we have a lot of question marks here, and generally we don't know how to take averages of question marks. So how do we end up doing that? Well, so I'll go through these two stages in telescope matching to kind of give you a sense of how this works. So in the first stage, what we're going to do is we're first going to subset to a particular level of A. So we're going to say, first I'm going to focus on all treated units, or I'm going to focus on all control units, and then I'll iterate between the two. So for instance, here I'm focusing on just treated units, or control units. And I have a one column that has m equals 1, and one column that has m equals 0 for these six units. And just to add to confusion, apologies, but these are not the same 6 units as we see before. These are just slightly different example. We'll come back to those. So what we're going to do is we subset to a particular level of A, and then we're going to match each of the m equals 1 units to the closest m equals 0 units in terms of their values of the baseline and the intermediate covariance. So basically, we're just going to find the closest, the kind of nearest neighbor units across levels of m. And then what we can do is and in this case, like maybe it's the case that y1 is matched to y2, y3 is matched to y4, and y5 is matched to y6, right? And we're going to impute, right? Because, for instance, we don't get to observe for unit 1 what they would have had under y00, right? So what we're going to do is we're going to impute that missing potential outcome for them using the value that we do observe for their matched unit, so y2. So for instance, you can see here that what's going on is that we're going to use y2 as kind of our best guess about what would have happened to y1 if they had 0, 0. We're going to use y4 as our best guess about what would have happened to y3 if they had 0, 0. And we're going to use y6 as our best guess as to what would happen to y5 under 0, 0. And that's really, so that's that we're basically going to create this new kind of a transformed outcome, which is going to be if you already have m equals 0, you get the unit, we get to observe your outcome, and so that's fine, right? But if not, if you're m equals 1, we're going to kind of substitute your value of your nearest neighbor for that potential outcome, and this is going to give us a column of data, which is basically our best guess as to what each unit would have done if they had m equals 0. Okay, so just to give you a sense of how this works in this particular example here in this data, right? So we have this column of y1 of 0, and we're going to focus on just the treated units here for a second. And so I'll just gray out everything else. And so basically we have one m equals 1 unit 1, and we need to figure out we need to somehow impute their missing potential outcome. So what we're going to do is we're going to find the closest unit that has the same level of A, and that is the closest in terms of x and z, right? And so you can see here that if you look at these 3 units that all have that all have A equals 1, the closest unit to 1 in terms of its covariates is going to be unit 2, right? So we just go ahead and impute the missing potential outcome there with the value y2. Right, so now we have, at least for these treated units, we have best guesses about how each of these values is going to respond under units is going to respond under one kind of treated units with low levels of anxiety. Okay, so that's the first stage, and then the second stage is going to be basically a standard matching procedure. That's going to, right, so if you look here, we haven't quite filled out this column yet because we need to match all of the units, the treated units, to all of the control units. So we don't have, none of our control units yet have any potential outcomes here. So we need to somehow impute the rest of this column. And so that's where the second stage comes in. And what we're going to do there is we're going to use basically a standard matching technique, a standard matching approach that using this kind of transformed variable that I was just discussing as an outcome, completely ignoring the mediator and the z. So we're just going to now treat those as if we don't have them for analysis, and we're only going to focus on A and X. And in particular, right, we're going to match each control unit to its closest treated unit, in terms of their X values. And then we're going to impute the missing potential outcome Y10 for those control units using their matched treated units. And we're going to match each treated unit to their closest control unit in terms of their baseline covariates. And again, we're going to impute the missing value of the potential outcome under 0, 0 for those treated units. Right. And so then what we do is now once we do this, we'll end up with we'll have two columns that are completely filled out in the data, and we can just take the difference, the sample difference in means between those two columns as being our estimate of the control direct effect. Right. So in particular, right, so we have these two columns, and what we can do with them, again, we need to match across levels of A. So from A equals 1 to A equals 0. Right. And if we think about now, we're going to ignore the values of Z and just try to find among the control units here, we're going to try to find a value that we're going to try to find a treated unit that is the most similar just in terms of X, right? And so when we do that, we can see that the closest value for unit 4 is going to be unit 3. The closest unit for unit 2 is going to be unit 5, for unit 5 is unit 2, and then the interesting one here comes with unit 6, right? If you look, its closest match is going to be unit 1, right? And maybe you think we should put in the value, it may be intuitive to put in the value of just unit 1's outcome. But remember what we're doing here is we're actually going to use unit 1's imputation instead of its potential outcome. And so when we match unit 6 to unit 1, we're going to fill in its value with its own imputation. So what you can see can end up happening here is there can be these indirect matches, so that unit 2 is matched to unit 6 indirectly through its kind of first stage matching in unit 1, right? So, but this is basically how this procedure works, and we can apply the same idea to the Y00 column, right? And now what we've done is through this matching, we've created an imputed columns that are the potential outcomes for each unit in terms of how they would have responded under, say, treatment, low anxiety, and control, low anxiety. And we can just take the difference between each one of these columns, in the rows of each one of these columns, and divide by the number of units to get our estimate of the control direct effect, right? The effect of the treatment for low levels of anxiety. Okay, so why do we like this estimator? So we like this estimator because it's simple. It's basically two standard matching steps. Both can be done without access to Y, so you can actually do both of the matching procedures before you even see the data, so that can avoid some p hacking if that's something you're interested in doing. I hope you are. So it's a consistent estimator. So we've shown that we've proven the paper that this is consistent for the average control direct effect, and basically under some regularity conditions, this converges asymptotically. It is biased, right? So basically, even though it's consistent, it is biased, and that's because the bias term actually converges to 0 very slowly. This is very similar to a standard matching procedure. The end result of that is that this doesn't converge asymptotically to a normal distribution. And so basically, what we do with this is we follow Abadi and Emmons, and develop a bias correction procedure that uses a little bit of regression to kind of tune up our estimates. And what we like about this is it's robust because we think that it's more, and we show in the paper that it's more robust to model misspecification in at least some deviations from the modeling assumptions. So that's all great, but we also like to have standard errors associated with our estimates. So one problem with this is that the variance of this tau hat is like super complicated. So trying to like write it down is very hard, and trying to estimate it is even harder. And that's because basically each unit could be matched multiple times at each stage. And so that means that the tau hats are not just the sum of kind of a bunch of IID random variables. And that's kind of how we do central limit theorems. And so that makes kind of calculating the variance of this pretty hard. Unfortunately, our first go-to would be to say, like, maybe we can just bootstrap it. But it turns out that Abadi and Emmons have shown in another paper that kind of naively resampling rows in kind of in a standard non-parametric bootstrap doesn't give you valid matching estimators. So you don't actually get the kind of nice, you can get actually bias in terms of your estimated standard errors and confidence intervals by using matching and a bootstrap together, at least a non-parametric bootstrap. So our approach in the paper is to follow a recent JASA paper that looks at using what's called the weighted bootstrap, And instead of, say, re-weighting rows in our data, what we basically do is figure out what contribution each unit makes to the overall estimator, and then resample those contributions. And what that does is it actually just sidesteps some of the problems we see in the abelian and bins approach, and allows us to kind of get a non-parametric, or basically non-parametric variance estimate. So that's a nice feature. Okay, so I was just going to go through a quick simulation to kind of show you that this can actually matter in a lot of situations. So here's a basic simplified version of this DAG. There's this graph, and this is going to be the setting for the simulation. And so we have two baseline covariates, x1 and x2, one intermediate covariate z, and we have an unmeasured confounder between z and y. So even though it's unmeasured for the relationship between z and y, controlling for z blocks the confounding due to this variable. And so sequential ignorability holds in this particular case. So here we've constructed the situation where the true control direct effect is 0. So the effect of A on Y only goes through M in this case. And the delta here, which is the kind of the coefficient between U and Z, is going to control the amount of post-treatment confounding that's going on. So this kind of measures kind of how bad it would be if we omitted Z from the regression, and how bad is the confounding between M and Y. So when delta is not equal to 0, controlling for Z in a naive regression is going to induce post-treatment bias, which we want to avoid. And so the last kind of step of this is that we're going to go ahead and we're going to think about how do we think about doing model misspecification. And so that's kind of like a hard thing sometimes to think about simulating, because usually we kind of assume that we have the right model. So we're going to follow Kang and Schaefer, who did a great set of simulations. But what they did basically was they did nonlinear transformations of each one of the covariates, and then pretended that us as simulators or as the analysts only had access to the transformed variables, not to the original variables that are actually in the data generating process. So in particular, right, we have x1 star, which is exponentiating x1, and then we have a crazy nonlinear function of x2, and z is also going to be transformed in this particular way. So in a model, when we have model misspecification, that just means the analyst only has access to x star and z star, not to the original actual variables from the data generating process. So we're going to compare this to kind of a naive regression that's going to condition on everything. We should expect that to be biased due to post-treatment bias when there is post-treatment confounding. We're going to think about sequential G estimation, which is this kind of structural nested mean models when everything is linear. Right, so that's just a kind of a version of this regression setup. And then we're also going to look at this telescope matching with the bias correction that I mentioned. And so we'll just go through each of those and kind of show you how the results look for each of these. And just the number of matches that we're going to do at each stage. Like I showed you earlier, kind of 1-to-1 matching. So we find the nearest unit, but you could have variable matching numbers. And so we're going to have 3 matches in each of these stages. Right, and so just to focus on the bias to begin with, this is going to be so what I'm showing you here are 2 different panels. The panel on the left is going to be the correct specification. That's when we actually know the true values of x1, x2, and z. And then on the x-axis is going to be varying how much post-treatment confounding there is. And on the y-axis is just the absolute value of the bias that we get from these simulations. And this is a sample size of 2,000. And what we can see is that kind of on the left side in the correct specification, when there's 0 post-treatment confounding, the linear regression, just including the mediator, does a really great job, right? 0 bias, very close. But as soon as we start to deviate from that, we have some post-treatment confounding, so some relationship between, some confounding between M and Y, we start to see that bias gets pretty bad by just kind of naively controlling for everything in the regression. And this bias, unsurprisingly, when we have the incorrect specification, we see bias at all levels, but it still increases in terms of its in the post-treatment confounding. Sequential G estimation, on the other hand, very nicely does a good job in terms of when we have the correct specification, it is resistant to this kind of post-treatment confounding. So it doesn't really matter how much post-treatment confounding there is. It is basically unbiased in the correct specification. But in the incorrect specification, we can see that there's a large increase in the amount of bias for that approach. And so the idea behind this, and so telescope matching has this nice property that, again, in the correct specification, we're seeing that it's essentially unbiased after we do this bias correction across levels of the post-treatment confounding. But what's really nice is that even when we have the incorrect specification, so we don't have access to the right transformation of the data, we just have kind of we don't know the true functional form. We see a pretty large reduction in the absolute value of the bias, and that kind of actually goes down a little bit as post-treatment confounding goes up. Right. And so how, like, where do we pay the price on this a little bit? We can see that, one thing we can see with this is we can kind of see that this is just root mean square error and see for instead of bias on the y-axis now. And what we can see is that first of all, linear regression kind of is just following its bias trend. We can see that sequential G estimation you pay a little bit of a penalty in the correct specification. It has higher variance, it looks like, than linear regression, and it kind of does worse a little bit as you increase the amount of post-treatment confounding because the uncertainty goes up. And we can see that, again, under the correct specification, the root mean square of telescope matching is a little bit higher than sequential G estimation, and that's kind of getting at this idea that it's a little bit less efficient than kind of knowing when you know the correct model. Right, but the big gain is that when you don't know the correct model, you can do a lot better in terms of bias. So this is, again, just a similar type of bias variance trade-off here in terms of how well do we know the functional form versus not wanting to make that assumption in any particular case. So the kind of last thing I'll go through is this actual application to a real data data set, so a real replication. So this is the Brader, Sue, and Valentino project. So there again, the idea here is we're looking for the effect of media messages on support for immigration, and in particular, the main effect of interest here was a story with a negative tone and a non-white immigrant showed reduced support for immigration in their experiment. So it's this idea versus positive versus negative tone. That's the kind of main treatment of interest for us. And so the question that we are tackling in this replication is, does the treatment we have data on a particular mediator, which is anxiety, and there's some evidence that treatment actually affected the levels of anxiety. And so can we determine if there's an effective treatment that remains even if the mediator is anxiety mediator is held fixed? So is there kind of an additional effect beyond just its path through anxiety, or does it seem like anxiety is doing most of the work? Kind of a standard mediation analysis in this setting might be suspect, because there we would need there to be no post-treatment confounders for the relationship between M and Y, like not even observed, unobserved, anything. And so here we are allowed to have those confounders as long as we can control for them. So in this, what we'll use for pre-treatment confounders are going to be education, gender, income, and age. And the post-treatment confounder in this particular case is going to be the perceived harm due to immigration. Right? So this is just another post-treatment variable that measured the harm that was perceived by the respondent. And so here we're going to compare a lot of different effect estimates, or for in particular, the first is just going to be the average treatment effect. And what we can see is that, again, the positive tone had an effect on increasing support for immigration. When we look at the naive regression, again, which just kind of throws in the Z and the M all into the same thing, we see that is reduced a little bit, but we still see a positive direct effect of the treatment even after conditioning on anxiety. Even when we do sequential G estimation and kind of make sure that we're not doing anything crazy with post-treatment bias, we still suggest a non-zero direct effect, even if we fix that level of anxiety. But when we go to telescope matching and we actually just find matches for this, what we see is that the control direct effect is much closer to zero, and we have much more uncertainty about our estimates. Right? And so that can happen a lot, where once we weaken some of these assumptions, it could be the case that a lot of the work in the sequential G estimation or these kind of model-based approaches is really being driven home by kind of maybe some artificial assumptions. And once we weaken those assumptions, we see a lot more uncertainty about our estimated effects. We have other replications where we see this kind of where things go from being not significant under sequential G estimation to being significant at telescope matching. So it doesn't necessarily have to go in this direction, but the kind of finding that the variance gets bigger is both consistent with the simulations and what we expect given the setup. And so one interpretation of this, although there's high uncertainty, is that it looks like fixing the mediator. So fixing the level of anxiety eliminates most of the treatment effects. But again, high uncertainty. So just to wrap up, kind of standard matching and standard regression approaches, unless really strong assumptions hold, don't really work for direct effects in this way. So, and the models that do exist, such as structuralness and mean models and inverse probability of treatment weighting, are really model dependent. So what we try to do in this paper is introduce a two-stage matching procedure to close this gap that both handles direct effects in the right way, but also is a little bit less model dependent. It's a consistent estimator. It's a little biased. So we use a bias correction. We use the weighted bootstrap for uncertainty estimates. The next steps for us in terms of things that we're thinking about are trying to get better variance estimators to handle some undercoverage in small samples. So we have a little bit of undercoverage when the samples are really small. So the actual coverage rates are slightly smaller than the nominal coverage rates. And we're also working on a way to apply these ideas to mediation analysis. And so in mediation analysis, we don't have any intermediate confounder Z because of the assumptions of those approaches. And so we can think about basically trying to tweak this method to just do it maybe in a more straightforward way when there are no intermediate confounders. And then also, we have to think a little bit about, we don't drop any units in this particular, in the first stage of this approach. So we don't do any pruning in the first stage. Because if we did, it could induce post-treatment bias. So one question for us that we're kind of thinking about is how might we do that in a principled way? And so that's all I have for you, and I look forward to your questions.
Okay. Thank you, Matt, for that presentation. At this point, Matt Blackwell is available to take questions from the audience. You can ask a question using the Zoom Q&A button that appears at the bottom of your webinar window. And when I see a question, I'll just go ahead and read it out. While we're waiting for questions from the audience, I have a couple of questions. So stage one of the indirect or of the telescope matching estimator seems pretty it makes sense to me.
Yeah.
I really don't understand stage two though, and let me explain why. So actually, it would help if you could scroll back in your presentation to when you're actually making those matches. That the example is really helpful here.
Sorry.
Yeah, it's pretty far back. Yeah, there we go. There we go. This is great.
Yeah.
So when you make the matches in the second stage, when I just sort of look at this, if I don't know what else is going on and I just look at what's going on here, what I think is, well, wait a minute, why would it be valid to impute Y3? Okay, so I guess the assumption that we're making here is that if unit 4 were to be treated, it would have the exact same outcome as unit 3 if it also had a different value of the mediator. Right? In other words, if the mediator value and the treatment value were to both change, everything would be the same, or it would be pretty close to being the same.
Yeah, so it's a little bit, it's a little, yeah. So I think the way we're kind of thinking, the way you may want to think about it here is that, we're trying to find all we're trying to do in this case is try to find the treated unit that is the most similar to unit 4 in terms of its baseline covariates. Right? If that's true, if we can find that unit, then those units should have similar potential outcomes, right? Because potential outcomes are pre-treatment to everything. They're just like these fixed things about people. And so the idea is that what we can always do is if they have very similar values, then we should be able to just like kind of use as a best guess, or at least as like a prediction, the potential outcome for unit 3 should, if they're like the same in terms of X, they should have the same potential outcomes on average. And so kind of using one for the other is going to matter no matter what the actual observed value of M was for those two units. Now we had to have M equals 0 for unit 3 in order to be in this column to begin with, so to speak, for unit 3 to their imputation in this column to be Y3. But yeah, so we're going to ignore that information. The fact that they're different on M doesn't we ignore that for this step.
I'm curious about so the thing that makes this really hard is Z, right? Because there are things that essentially confound. You call them confounders in the mediation part of it.
Yeah.
I would almost call them, or the way I was thinking about them is unmodeled mediators. Yeah, right, because they are mediators.
Yeah,
and also there's interaction among the mediators. That because Z affects M. It's an unmodeled mediator that affects another mediator. I know that there's been some scholarship on interaction between mediators, and that creates some sort of special problems. How does your approach interface with that other work?
Yeah, so generally, so it'd be something like, Kosuke Mai and Teppei Yamamoto have a paper where they kind of extend their other work on mediation to the case where you have multiple mediators. One key difference is that they're really focused on these mediation quantities of interest. So basically, these ways of being able to partition out, the total, what proportion of the total effect is due to this mediator, that mediator, this other mediator, and so those can include those direct effects are part of that, but they're actually confusingly that's a slightly distinct quantity of interest from what we're doing here, and they typically require stronger assumptions. So you would, for instance, in that kind of setting, you need the relationship. You need those other mediating variables to be themselves have no unmeasured confounding, right? So there needs to be kind of or no confounding. So at some point, the confounding needs to stop in order for that to work, and you need to make some kind of roll it back a little bit. Whereas here, we take a much more agnostic view about these Z's and whether or not the effect of them is identifiable at all. That's essentially why we're thinking of them as confounders. We're not thinking of them as direct interest. They could be, and so you need a different approach to do those. To analyze that, but in particular, we're going to think about them as just kind of confounders because we're being more agnostic about the idea of whether or not we can identify their effects. Whereas, say, Kosuke and Teppei are going to think a little bit more about making assumptions that would allow you to estimate all of the effects, like all the arrows, essentially.
We have a question from the audience. This is from Aaron Ehrlich. Can you give us more intuition about how you think the number of matches M, or how you think about the number of matches M, and how that varies by sample size or any other aspects of the data?
Yeah, so I think, so the trade-offs with, so the standard trade-offs apply with kind of matching and the number of matches. So, you have a low number of matches, you tend to have better matches, but you have a smaller effective sample size at the end, and you may have to, in a setting where here there's a little bit less of a concern because we're not actually, it's only a concern in the second stage because we're not pruning anything. So if you had in the standard approach, if you have like a caliper match, then you're going to drop units that are not close, and so having multiple matches can be helpful. So here, having a small number of matches gives you kind of high quality matches, but it could get you a little bit less variance. As you increase the number of matches, obviously you're getting farther away in terms of kind of how similar the matches are. Because the first match was the best, that's why you matched it, and then the second and third and the fourth, they're getting progressively worse. So you can introduce a little bit more bias as you increase the number of matches, and you can make up for it. And so you make up for it a little bit in terms of the variance. So one way that it's helped in our approach is that we apply on top of this matching, we apply some regression to help kind of smooth out some of these issues, basically doing regression on the matched groups. And that allows us to kind of work things out a little bit. We don't have great intuition yet about exactly how many matches. And especially one thing we're trying to figure out is matching across the two stages doesn't have to be the same in terms of the number of matches. So it might be the case that the number of matches in the first stage should be or can be different than the number of matches in the second stage. And just trying to do the analysis in terms of the efficiency, the formal efficiency analysis of that kind of setup is really hard. And so we simulated a little bit. I said three. One reason why we use three, and the example is it seems to work pretty well. Beyond that, you do get some degradation, but I don't think that's like a totally. That's not something that is like that's unique to maybe this data set or our simulations. And yeah, I mean, one other thing to think about is that as the sample size grows, I mean, so the asymptotic analysis, the kind of theory that we have in this paper is based on letting the sample size grow to infinity and fixing the number of matches. But another way to think about this, you could kind of, another way to do things is that if you were to kind of increase the number of matches as you increase the sample size, that would look more like kind of a local regression or local non-parametric regression. And you might be able to you might be able to get some efficiency gains there. It's just more complicated, and we don't have a great way of kind of choosing the number of matches as the sample size grows. So, that's just another. You could do that, and you may get some. So in very large samples, you maybe do better with higher number of matches, but we don't have the analysis to kind of show that.
This is a sort of related question, and it also bears on the first thing I asked. So in the second stage, you're only matching on X, not on Z.
Yeah.
But looking at your sort of causal diagram that I sketched out, it would appear that including Z would make it harder to get matches, probably, or
yeah.
But wouldn't it improve the quality of the match in the second stage? Why isn't Z included there?
So the key reason why we don't want to include M or Z in those matches is just because by doing so, we could be inducing post-treatment bias, right? Because we're implicitly what you'd be doing is conditioning on Z in terms of
Z influences M. That's the problem.
As Z influences M, Z influences Y, and Z is influenced by A. And so we just don't want to match on that post-treatment. Post-treatment in this case meaning A. We don't want to match on that post-treatment.
I understand. Yeah. So I was looking, and I didn't actually realize until you mentioned it that bootstrapping is invalid for matching type estimators. But I was sort of looking at the paper really quick while you were talking, and it looks like certain kinds of bootstrapping, maybe block bootstrapping, could work. Did you try? Is there some sort of block bootstrap that would work in this case?
There's some techniques that are like it's actually really to me it's really unintuitive, but actually there are some techniques like subsampling, which is actually not like maybe people are familiar with it, but basically what it means is you sample a group that's less, you have to do resampling on a group that's less than the size of the data. So kind of like bootstrapping, but not as much data, which seems unintuitive because it seems like, why would you want less data? But it turns out that kind of helps this problem along. We haven't quite put those things. In fact, actually, one thing we found in simulations that the non-parametric bootstrap doesn't do too bad, at least in our simulations. And again, I think that's a function of our simulations. What really goes wrong in this is that the bootstrap distribution doesn't preserve. What's ended up happening is that you end up, if you have repeat units, that are matched, in your bootstrap, those get matched multiple times, which is kind of artificially and so what ends up happening is that the distribution of how often each unit is matched doesn't get preserved in the bootstrap distribution. And so basically you just need some way of figuring out, and Imbens and Abadi and Imbens have some ideas about doing that. There's weighted bootstrap is another way to do that. But yeah, I mean, we've done the weighted bootstrap, the non-parametric bootstrap. And I don't think we've quite worked on the kind of subsampling. It's a little bit more computationally intensive.
Stephen Finkel asks, do you also need the difference between columns 1 and 3, this is, I assume, in the thing we're looking at right now, to get the control direct effect when M equals 1, or is that not relevant to the quantity of interest?
Yeah, so I mean, so there's however many levels of M there are control direct effects estimates. So you could be interested. So I kind of in the presentation, I just focused on the control direct effect for M equals 0. But you could also be interested in the control direct effect for M equals 1. And in that case, the only difference between that is that you just have to change how you're doing the first stage matching. So in the first stage matching here, what we did was, if I kind of go back, what we did was we matched each M equals 1 unit to its closest M equals 0 unit, and then use that to impute the value that we, of M for M equals 1 units, what they would have had under M equals 0. So we usually go the other way around. So just find for every M equals 0 unit, find its closest M equals 1 unit and impute things that way, and you just end up with, that's how you end up imputing these other the other columns here. And so you can do kind of two matching procedures, two-stage matching procedures to fill out all the columns in this data and estimate all of the different quantity, both of the control direct effects. And sometimes that's of interest if you want to say, are interested in like thinking about the interaction between these two things and whether or not it's different at different levels of the mediator. And that can be another kind of way to kind of suss out whether or not what you think is going on in a particular empirical setting.
Okay, well, I think all the questions have been answered, so I'm going to go ahead and call it just a minute or two early. That's all the time we have. I'd like to thank Matt Blackwell for being our presenter this week. I want to mention that his presentation will be posted to our website shortly after this broadcast. If you'd like to share the presentation with a colleague or watch it again later, you can do that. I also want to let you know that on Friday, October 19th, that's next week, we will host a talk from Masha Kropenkin of Stanford University. The talk is entitled The Advantages and Limitations of Using Individual-Level Web Search Data to Study Political Behavior. Please visit our website, www.methods-colloquium.com, to get more information about this talk. Matt, thanks very much for being on today. I appreciate it.
Great. Thank you so much, Justin.
All right. Thanks, everyone. See you next time.